If in the near future we detect oxygen on one of the exoplanets in a habitable zone, would it be a proof that the planet has life? How can Earth cyanobacteria help us to answer this question? How did the grandparents of the Sun, so-called population 3 stars, the very first stars in the universe, look like? Can they solve one of the long-standing puzzles of the modern cosmology? To learn the answers, watch this second episode of my new weekly podcast, Astro Edge.
Welcome to Astro Edge, weekly broadcast presenting highlights of leading-edge research in astronomy and astrophysics.
First paper we'll cover today is Oxygenic photosynthetic responses of cyanobacteria exposed under an M-dwarf starlight simulator. Implications for exoplanet habitability. The first author of this paper is Mariano Battistuzzi. He is from University of Padova, and the whole team is from Padua, Italy. Let's disassemble the title. It sounds a little bit scary. Let's just disassemble piece by piece to understand what they're talking about. First piece of the puzzle is cyanobacteria. What are cyanobacteria? Obviously, it's a kind of bacterium which obtain energy via photosynthesis. And that way, they're similar to plants. Plants get energy to live from absorbing sunlight, so-called photosynthesis. This is one important part about cyanobacteria. Very critically, cyanobacteria are the first organisms known to have produced oxygen. Why oxygen is important? This is basically a discussion of a possibility of a life arising around other stars, and life as we know it, especially the complex kinds of life, including intelligent life, does require oxygen in the atmosphere. You can have some very primitive kind of life, like cyanobacteria or plants, which can exist on other planets. But without oxygen in the atmosphere, we think no more complex kind of life would evolve, in particular including intelligent life forms. So oxygen is critical, and we think cyanobacteria or something similar would be very important to have on other exoplanets if we are to discover complex life form or even intelligent life form around other stars. The next piece of the puzzle, the part of the title, is M-dwarf. M-dwarf is a kind of a star. It's in fact the most common type of star. M-dwarf stars also called red dwarf stars. As the article here says, red dwarf is the smallest and coolest kind of star. They're also the most common type of star. It is believed that red dwarf stars make up around 3/4 of all the stars in the Milky Way galaxy and other galaxies. And more specifically, M-dwarf stars, they're the smallest among them. A bit larger ones are K-dwarf stars, but we are focusing here on the smallest, on the faintest red dwarf stars called M-dwarf stars. And the third part of the title, which is critical, is habitability. Habitability is a term used to describe exoplanet. So what is exoplanet habitability? As this article describes, for an exoplanet to be habitable, it has to be just at the right distance from its star. Let's take solar system as example. Our Earth is obviously habitable. It's the only habitable planet we know. If you take Earth and push it all the way at the distance of Mercury from the Sun, much closer, the Earth would start receiving much more energy from the Sun because it's much closer. So it will get overheated and all the oceans will evaporate. So it will become non-inhabitable. If we do the opposite thing, we push Earth all the way to the orbit of Mars, 50% further away from the Sun, there is more than factor of 2 less sunlight, the Earth would get much colder, the oceans would freeze out, again it would become uninhabitable. So there is a fairly narrow range of distances in the solar system where our Earth would be able to maintain liquid water. And that's what defines habitability. The life as we know it requires water, requires oceans on the surface. To have any chances finding of life around another star, on an exoplanet, at the very least we want to make sure the liquid water can exist on the surface. Otherwise, we think life just would be impossible, at least as we know it. So that was example with our sun. So let's take example of a red dwarf star. A famous example of a red dwarf star is Proxima Centauri. Proxima in Latin means closest. This star, in fact, is the closest to us. It only takes around 4.5 years for the light to reach us. Despite its closeness, it's actually a very faint star. Its magnitude around 11, so you need a fairly large amateur telescope to be able to see it. Plus, you need to be in the southern hemisphere. It is an M-dwarf red star. It's M5, and the faintest red dwarf stars are M8, M9. M5 is kind of middle, halfway, so it's pretty faint and it's pretty red. It's sort of classical M-dwarf star. What if we take Earth and place it near the red dwarf stars such as Proxima Centauri? What's going to happen? Red dwarf stars are much, much fainter. As you can see here, it's only 0.0056% as luminous as Sun. As a consequence, if we take Earth and bring it near that star, we have to place it much, much closer than the current distance from the Sun to be able to keep water liquid on its surface. So we did discover a planet B, exoplanet, near Proxima Centauri, which is only located 7.5 million kilometers from the star, which is 4.7 million miles. And to remind you, Earth is 150 million kilometers from the Sun, around 90 million miles. And this is the habitable zone. So this is how close Earth needs to be placed near red dwarf star to have a chance of having life evolve there, to have a chance of liquid ocean, liquid water on the surface. So now we are putting together all these three pieces of the puzzle. We want to figure out whether cyanobacteria can exist or even thrive on habitable planets around M-dwarf stars. We are particularly interested in M-dwarf stars because there are by far the most numerous type of stars and most of exoplanets, and especially habitable exoplanets, rocky planets within a zone where oceans can be liquid on the surface, is dominated by M-dwarf stars. So what did these researchers do? They created a starlight simulator. They created a special lamp which light copies very closely light from M-dwarf stars. It's a very red light, so there is very little of green, almost nothing of blue colors. It's mostly red. And then they took two kinds of cyanobacteria. There are all kinds of cyanobacteria, but they took two types. One of them has this designation, and this is the cyanobacteria which is already a good candidate for this situation. This is bacteria which is known to live and even thrive under conditions when there is mostly red light. It's called far red light photoacclimation. Still, they wanted to test it experimentally, whether indeed this will happen under actual M-dwarf light situation. And then they took another kind of cyanobacteria, which is much less likely candidate. This kind is known not to thrive under pure red light condition. So they did the experiment. They created a special lamp simulating M-dwarf light. They exposed two kinds of cyanobacteria. So what's the result? The result is positive and it's great. It's great for in our quest for searching for life out there. Our results experimentally show that an M-dwarf light spectrum could support a biological oxygen production similar to that in solar light. In particular, the cyanobacteria, which was already good promising candidate, did what it was expected to do. It thrived under the M-dwarf light conditions. Much less likely candidate also thrived. Researchers speculated this is because even though it's a red light, there is still enough of green light in the M-dwarf star spectrum to make the cyanobacteria a viable candidate to produce oxygen in exoplanet's atmosphere. So both more likely and less likely cyanobacteria candidates did a very good job in generating oxygen when exposed to M-dwarf red light. In conclusion, this research solved another piece of puzzle in our quest to discover life around other planets. It is known that it's not sufficient for exoplanet to be in the habitable zone, which is required to have liquid water on its surface to harbor life, in particular complex life forms like intelligent life forms. We also need oxygen. And the researchers tested two cyanobacteria which are known to contribute to the oxidization of our atmosphere a long time ago, which resulted to complex life forms evolving on Earth. And that's great news. We're not capable yet, but in the near future, we'll be able to see signs of oxygen around on other exoplanets, if they do have oxygen. And if we manage to discover oxygen on other exoplanets, Thanks to this research, we'll be more confident that this oxygen could have been produced by cyanobacteria and not due to some geological, non-biological process. So great contribution in our quest to discover life around other planets. In my book, this research does have an edge. The second paper for today is the most massive population 3 stars. The authors are Teeraparb Chantavat from Thailand, Dr. Siri Chongchitnan from Warwick University, UK, and famous astrophysicist Joseph Silk. Before I can explain to you what population 3 stars are, let's very briefly walk through the history of the universe. Here's the brief history of the universe, starting from the Big Bang, where everything was created in one giant explosion, and moving all the way to the modern times. Here's the axis of time. So a Big Bang happened 13.8 billion years ago. Right after Big Bang, universe went through extremely fast expansion called inflation. Then the universe, which consisted mostly of super hot gas and also dark matter, kept on expanding, and at some point became cold enough to become transparent to light we see today as afterglow, cosmic microwave background. This happened 375,000 years after the Big Bang. Then for some time the universe was dark. There were no stars yet, no galaxies. At some point dark matter became clumpy and started collapsing, making what we call halos, which would become future galaxies. The gas followed, so at some point we had dark matter galaxies full of gas, no stars yet. And at some point, which is still debatable, here it says around 400 million years, could have been a bit earlier, the gas in those first galaxies start fragmenting itself and result in formation of the very first stars in the universe. So this paper is actually about that, about the very first stars in the universe. But just to finish with the brief history, universe kept expanding, the galaxies kept forming, each galaxy had lots of stars forming. Another interesting thing was happening. Big Bang resulted in gas which is void of heavy elements. It's mostly hydrogen, helium, the two lightest elements in the periodic table of elements. But we know in the modern universe there are quite a few heavy elements. Astronomers call them metals. But they're in fact just anything heavier than helium. Things like carbon, oxygen, etc. Things which are essential for making rocky planets like Earth and essential for forming life on such planets. So where did we get these heavy elements? It happens that the very first stars which form from this pristine gas, we cannot see them, and that's the whole purpose of this paper. We cannot really see them yet directly through our telescopes. We can just speculate what they were. We can try to model them, and we think they are fairly large and massive, these very first stars, and because they were massive, they live short lives and then explode as supernovae. When stars age, they burn fuel, hydrogen, and the product of burning is heavy elements. This is how heavy elements were introduced in the gas inside galaxies. The very first stars started exploding, depositing the heavy elements into the gas. So the next generation of stars would be forming from enriched gas, and they would have these heavy elements inside them. And the further we go, the more heavy elements are in the gas, in the galaxies, and stars have more and more heavy elements. This brings us to the population stuff. Scientists classify stars into 3 populations, but they're basically generations. Somewhat confusingly, population 1 stars are actually the youngest. So Sun belongs to this population. These stars formed relatively recently, billions of years ago, but way after the Big Bang. At the time when there were enough of heavy elements, so our Sun has quite a bit of heavy elements, carbon, oxygen, and others. So we had rocky planets like Earth forming around the Sun, and we had life forming on one of these planets. Population 2 stars, they still exist today. They're sort of parents of population 1, parents of Sun in some sense. They form early in the universe, shortly after Big Bang. They do have some heavy elements, but not a lot. Most of them at this point perished. They exploded supernovae. What was left is just the lowest mass stars. The smaller the mass of a star, the longer they live. The heaviest normal stars, like all stars, live very short lives, 10 million years, and then explode as supernova. The smallest star consists of very small dwarf, red dwarf stars, and those can live extremely long, trillions of years. So again, to emphasize, both population 1 and 2 still exist around us. The population 3 is the earliest it's a speculative. We haven't seen it yet directly. We might be able to see with modern telescopes, but for now we just speculate what they were. So we speculate these stars formed from the pristine gas, devoid of heavy elements, from hydrogen and helium mostly. And because of this very special environment, they were extremely large, much larger than population 1 and 2 stars. By now they all perished because they're so massive, exploded as supernovae or turned into black holes, and that's why we don't see any of them around us today. In some sense, you can call it grandparents of our sun. Going back to the paper, the best prospects of trying to detect this enigmatic very first generation of stars is recently launched James Webb Space Telescope. As the paper describes here, most likely the telescope won't be powerful enough to actually see the very first stars in the universe, unless we are lucky and one of those first stars located behind strong gravitational lens. So what is a strong gravitational lens? According to Einstein's theory, if an object like a galaxy is massive enough, it will bend rays of light of objects located behind it. Here's an example. Here's the foreground massive galaxy. It's yellow. There is a small blue galaxy behind it. It's so far away that if not for this foreground yellow galaxy, we would probably not be able to even see it at all. But because it happened to be located exactly behind massive foreground galaxy, we now use this foreground galaxy as a giant lens. The rays from the background galaxy got bent and distorted. Most importantly, they were amplified. So this blue ring you see here is much brighter than the actual object would be if there was no foreground galaxy. It's also highly distorted, but scientists learn how to recover true shape of the object distorted by gravitational lens. Most critical here, this blue stuff probably wouldn't be able to be seen unless the foreground gravitational lens, the large yellow galaxy. So the paper says that it might likely be possible to actually see the very first population 3 stars if it happens to be located behind one of those large foreground galaxies, which would serve as a gravitational lens. There is a problem with trying to understand what were the very first stars in the universe, the population 3 stars. They form as extremely rare object. They were not forming en masse in large numbers until later in the history of the universe. Because of its extremely rarity, it's very hard to model accurately these objects. So the authors of the paper, instead of actually directly modeling gas evolution, formation of stars, etc., they relied on other people models of POP3 stars, but they also use so-called extreme value statistics. This is a branch of statistics and it deals with extremely rare events. Basically, if you know what are typical things look like or events look like, can you somehow predict how the extremely rare manifestations of the same thing would look like? It is used heavily in structural engineering, earth sciences, finance, traffic prediction, and geological engineering. So the authors took the existing models of reasonably typical population 3 stars, applied extreme value statistics to figure out how the extremely rare manifestation of POP3 stars look like, how the very first stars in the universe look like. So why are we interested so much in these population 3 stars? One reason I already mentioned. These were the stars which enriched the pristine gas in the universe, contributed some heavy elements which later were consumed by the next generation of stars, population 2, and then passed on to population 1, stars like our own sun. Heavy elements are extremely important for making planets and creating conditions for life appearance on planets. It's known from models scientists have that population 3 stars would live fairly short lives and die one of the 3 possible ways: as asymptotic giant branch stars, as supernova explosions, or turn into black holes. The focus of this paper is on the latter, on the possibility these extremely rare population 3 stars ended up being massive black holes. Why is it important? This is because of the existence of quasars in the early universe. The bigger telescopes we build, the further in the universe we can look, we find objects called quasars further and further away. So what are quasars? Quasars are cores or centers of very large galaxies where a supermassive black hole exists. A supermassive black hole sucks in gas from the rest of the galaxy. Once you have enough of that gas, it starts getting heated and starts radiate lots of light and X-rays and radio waves. It can also launch narrow jets, which can also be seen through optical and radio telescopes. And the problem is, as we build larger and larger telescopes, we start discovering quasars way too far in the universe, which was so young, where current models do not predict existence of such supermassive black holes. And when I say supermassive, these are millions or even billions of masses of sun. How did such supermassive black holes appear in the universe? We know that stars like population 1 and 2 stars, if they're large enough, like O stars, they end up their life as supernova and create a relatively small black hole. Masses, I don't know, 10 solar masses or 15 solar masses, something like that. We are less sure about how one can create a supermassive black hole, like millions and billions of masses of sun. And here, population 3 stars can help us. Through the analysis, the authors say, even though these objects they're dealing with, the very first stars, POP3 stars, were extremely rare, but they likely had extremely high mass, thousands or maybe up to 10,000 masses of sun. They ended up their lives creating a fairly massive black hole, maybe thousands of masses of sun. And those black holes, which are much larger compared to typical stellar mass black holes, as I said, it's 10 masses of sun or so, they could have been seeds of supermassive black holes. So once you create such a fairly large black hole, thousands of masses of sun, then it can start sucking in the gas, surrounding gas from the galaxy, and then can grow and grow and grow at fast rate. At some point becoming supermassive black hole, maybe billions of masses of sun, and at some point becoming a quasar, the ones we detect now in the early universe. Admittedly, this paper is not based on very accurate modeling. They don't use numerical gas dynamical simulations like other people do who model more common representative of population 3 stars. Because they're after the very extremes of that population, very, very rare events, it's hard or even impossible to model them using accurate simulations. Instead, the authors used a special statistic, extreme value statistics, and that allowed them to make interesting conclusions about the properties of these very extreme manifestations of population 3 stars. The important conclusion in the paper is that these extreme population 3 stars were sufficiently numerous, there were enough of them to solve the problem of existence of quasars in the early universe. In conclusion, we still don't know for sure how supermassive black holes appeared at such early times in the history of the universe. But the results presented in this paper suggest that one possible solution to this puzzle is population 3 stars. By studying their most extreme manifestations, the very first stars formed in the universe, the authors concluded that these very first stars in the universe resulted in the formation of black holes, which could have been the seed to make the giant supermassive black holes we see today as supermassive black holes. A very interesting result. This paper definitely has an edge. This is the second episode of my new weekly podcast, Astro Edge. Still an experiment. I'm still trying to figure out if I can make it in terms of amount of time it takes, and I'm still working, trying to improve the channel. I would really love to hear from you. Please leave a comment telling me where you're from, did you like the content, and any suggestions about how to improve the content would be highly welcome. Please don't forget to subscribe and give me a thumbs up. See you next time.